I am pleased to present to you the presentation Neural Network for Processing Experimental Studies of the Modulus of Elasticity and Hardness of Epoxy Composites containing aluminium 203, zinc ore, and polytetrafterotylene by Данило Стухляк, Олег Тотосько, Петро Стухляк, Олег Ясні, and Андрій Станько. In modern research on polymeric composition materials, artificial intelligence technologies, in particular neural networks, are becoming increasingly important as they can greatly improve the accuracy of prediction their characteristics. A neural network are a promising tool for prediction the mechanical characteristics of epoxy composite material. Their systems are able to effectively handle nonlinear dependencies, automate data analysis, optimize the composition of material, and adapt to new conditions. An epoxy oligomer ET20 was chosen for the study. For its cross-linking, a polyethylene polyamine hardener was used. The samples were formed by the method of hydrodynamic combination of components. Aluminum oxides, zinc oxides, and PTFE were used as fillers. These fillers have different surface energies. The introduction of oxide causes the formation of boundary layers with low molecular mobility around the filler particles. The intensity of linear microhardness and curing activation energy of epoxy composites depend on the content of metal oxides, which indicate their influence on the formation of the binder's mesh structures. The minimum activation energy of curin is observed at the content of 10 mass fraction per 100 mass fraction of aluminum oxide binder, which is due to the formation of a material with a more cross-linked mesh structure in the material. The latter provides high physical and mechanical characteristics of the composite material. The shift of the minimum toward higher concentration of the concentration curve for aluminum oxide compared to zinc oxide is explained by the difference of their surface energy. It has been proven that the introduction of both aluminum and zinc oxide at fluoroplastic reduces the degree of curing and the binder. At low levels of oxide filling additional structures, formation occurs due to the physical cross-linking, which contributes to the formation of material with a tire grid structure. The next step in the study of mechanical characteristics in the use of neural networks to process experimental data to model the results of hardness in PTFE and zinc oxide material. We used MLP192 multi-layer perceptron network. It's mean one hidden layer, 9 neurons, and 2 output neurons, and MLP172 for the aluminum oxide filler. For the three above-mentioned fillers are a function of the SOS type we used. The activation of neurons in the hidden layers was carried out using the logistic function for zinc oxide and aluminum oxide, and the tannin functional for PTFE. For the output layers, we choose the identity for zinc oxide and logistic for aluminum oxide and PTFE functions. The use of neural networks has significantly increased for accuracy and reliability of the results obtained, which is important in the study of mechanical characteristics of material. Artificial neural networks significantly reduce the impact of interference in experimental studies. They reveal hidden nonlinear dependence between strand parameters. The integration of neural networks with classical interpolation methods such as Akim method and splines ensure optimization of approximation parameters and adaptation for specific material properties. The results of experimental studies showed that the introduction of a relatively small amount of filler at temperature below the glass transition temperature contributes to the formation of local maximum of the material's elastics model. A further increase in the concentration of fillers leads to a decrease in this parameter. The analysis of the data obtained using various interpolation methods made it possible to establish that for more accurate modeling of the elastic modulus of an epoxy materials at temperature below the glass transition temperature, it is advisable to use the Akim interpolation method. This method provides high approximation accuracy and allows to adequate responding of the change in the elastic modulus in this temperature range. Built-in dependence between predicted and actual values is an important tool to assessing the accuracy of models created using artificial neural networks and help to identify the presence of symmetric errors. Analyzing correlation between predicted and actual values help to assess the level of generalization ability of neural network, which is important to ensuring its effective functioning on new data. It is also important to assess the distribution of errors, which helps to identify areas where the model does not work with sufficient accuracy and allow to adaptive adjustment of its structure or training algorithm. A comparative analysis of different neural networks architectures is performed choosing the optimal parameter and training algorithm that minimize forecasting error. The stability, accuracy, and reliability of the model are improved, which is prerequisite for its application in a real-world problem, in particular in predicting the characteristics of composite material. Here we see the prediction of experimental dependence of the elastic modulus E and the material filled with aluminum oxide, zinc oxide at a temperature lower than the glass transition temperature, and the elastic modulo ET of the material filled oxide aluminum and zinc oxide at the temperature higher than the glass transition temperature. So conclusion is that it was found that the maximum hardness of material was achieved when filling with a 6 to 8 mass fraction of aluminum oxide and 12 to 16 mass fraction of zinc oxide per 100 mass fraction of binder. The results of experimental studies have shown that the introduction of a relatively small amount of filler at a temperature below the glass transition temperature of the epoxy matrix contributes to the formation of local maxima of the material elastics models. A further increase in the concentration of fillers leads to decrease in this parameter. In this slide, we see the conclusion: the correlation between the predicted and experimental values of physical and mechanical characteristics was established. It is proved that the study of properties of the composite material, the characteristics of which change radically under the influence of the type of concentration of the field, is more experimented to use the Akim method, with more accurately reflect the behavior of the material. The application of the interpolation method in combination with the post-processing of the result using artificial neural network helps to significantly improve the accuracy of the original data and provides a high level of correlation between the experimental and prediction values. Thank you for your attention.